The second problem that we have put up on the board is from the mean value theorem, but I have carefully worded and selected a rather unusual problem for Rolle's theorem, because normally the Rolle's theorem problems which students are accustomed to solve are to find a C, to check for continuity, to check for differentiability, and to check for the existence of a C, and wherever possible to demonstrate that the value of C that one obtains is indeed between the A and B, but well inside it, that means in the open interval A to B. Now, this at first sight does not give any flavor of Rolle's theorem, but nevertheless, after the problem is solved, we will see that it's a very interesting and rather unusual problem from the Rolle's theorem category of problems. Now, we will rub out the inessential parts and leave the essential parts, and in fact take it up on the board. We will take it to top. So, we have been asked to find at least one interval in which a root of 3x squared minus 12x plus 11 is equal to 0 must lie. At least find what is at least one interval in which one root of this must lie. Now, we have to revisit the statement of Rolle's theorem as it is discussed in the theory of equations. There is a very special branch of mathematics which is very interesting, that's called the theory of equations, mainly dealing with polynomial equations and how to solve, for example, a quadratic. The Siddharacharya method is quite well known. How to solve a cubic, the Cardan's method is very well known, and how to solve a fourth degree equation by the methods of Ferrari and Euler. But we will just dwell on simple equations. So, here we have put up on the board a quadratic equation. Now, a student who is alert will see that this fellow is the derivative of capital Fx equal to x cubed minus 6x squared plus 11x minus 6. If this is a parent function, then this is a derivative function. This much is clear. If we derive this, it's 3x squared minus 12x plus 11. The minus 6 is given because alert students will now recognize that this fellow is nothing but x minus 1 into x minus 2 into x minus 3. And we will try and see how the parent function graphs. Then we will get back to the mainstream problem. For those of us who have graphed this function, we see that it goes something like this. If this is 1, this is 2, and this is, so we will take wider spaced values so that the graph turns out to be very nice. This is the x-axis, this is 1, 2, and 3. Now, this is 2, this is 1, this is 3. These are values of x. So x is equal to 1 here, x is equal to 2 here, and x is equal to 3 here. Use a different color chalk, things will emerge nicely. Now, Rolle's theorem as applied to theory of equations is stated as follows, which one is very evident also. Between any two roots of a function fx is equal to 0 of an equation, between any two roots of fx is equal to 0 must lie at least one root of f dash x is equal to 0. That means there must be at least one c between any two roots of a polynomial equation where the tangent will become parallel to the horizontal axis. Now this is slope function becoming 0. So we have f dash c is equal to 0. This is one c1 we can take, and here there is another c2. In this particular case there are two c's. Now the function graphs like this, that is also very evident. It is a polynomial, so it can't have kinks. It must have maxima, minima. We can check that when x is less than 1, all these three are negative. So the value of the function is negative. When x is more than 3, to the right of 3, all these terms are positive. So the function is positive. Now when we are between 1 and 2, say 1.5, this is positive, this is negative, and this is negative. So positive, negative, negative, that is positive. So the function is again positive. By similar reasoning, when x is between 2 and 3, this is positive, more than 2, this is negative, and this is positive. So the whole sign is negative. So by those considerations, we can see how this particular graph varies. Now the rest of the work is very simple. We can assert that between any two roots of this equation equal to 0 must lie at least one root of f dash x is equal to 0, which is our equation, this one. And the two roots or the three roots are 1, 2 and 3. So if we take one interval 1 to 2, and another interval 2 to 3, then we can assert that there is a root between 1 and 2 where C1 will lie. C1 lies between 1 and 2 and C2 lies between 2 and 3. In fact, we will solve this equation by a very elementary method and see that the C1 and C2, which we are asserting to lie between 1 and 2 and between 2 and 3, indeed turn out to be so. So you just rub out this, keep the diagram as it is. To solve this equation, 3x squared plus 11 is equal to 0, which implies 3 into x squared minus 4x plus 4. I have added 12 inside, so plus 11 minus 12 is equal to 0. It's very clear. I had 3x squared minus 4x. I put a 4 to complete the square, and then that means to the original expression I have added 12. I must take away that and bring this 11 down. So in other words, this is going to tell us that 3 times x minus 2 whole square is equal to 1. 12 minus 11 implies x minus 2 whole square is equal to 1 by 3. If that be so, then x minus 2 is plus minus 1 by root 3. So we can write down the values as x minus 2 is plus minus 1 by root 3, which means x is equal to 2 plus minus 1 by root 3. Now 1 by root 3 is about 10 by 17.6. 1 over 1.73 to 1 is 10 over 117 point something. We approximate that to 10 by 17, and that is about 0.6. 10.2 over 17 is 0.6. So 10 over 17 is taken as 0.6. So our two values are 2 plus 0.6 or 2 minus 0.6, that is 1.4. This value and this value, this lies in this interval and this lies in this interval. So C2 is 2.6 and C1 is 1.4. So we have squarely proved that there is an interval, there are two intervals we have come to, and we found that the C's indeed lie in these two intervals.